In 2013, an amateur radio astronomer in the United Kingdom detected a rhythmic, drifting transmission on the 237 MHz band. Analysis of the telemetry data traced the signal back to the Lincoln Experimental Satellite 1, or LES-1, a machine lost in orbit since 1967. Launched in 1965 as part of an early military communications program, the satellite failed to reach its intended trajectory and was officially declared dead 2 years later. This detection presents a specific engineering paradox. 50 years of exposure to unshielded cosmic radiation and extreme thermal cycling should have degraded 1960s-era components beyond any functional state. Standard chemical batteries have a definitive lifespan. Over 5 decades, the internal chemistry leaks and shorts, which should make any electrical transmission physically impossible. To understand this broadcast, we must perform a forensic gap analysis, tracing how these specific 1960s components bypassed their own physical breakdown. The recovery of LES-1 suggests that the heavy, discrete architecture used in early spaceflight inadvertently created circuits capable of maintaining electrical viability across decades of dormancy. Orbiting above us is a live, electrically persistent network of sleeping machines. At MIT's Lincoln Laboratory, engineers developed the LES-1 using the era's standard architecture, discrete electrical components, and point-to-point patch cables. The mission was designed to test high-frequency military communications, with the satellite positioned atop a solid propellant rocket motor. During orbital insertion, a wiring logic error in the onboard circuitry prevented the final rocket stage from firing. This error left LES-1 stranded in a tumbling, suboptimal orbit, where it could not deploy its antennas or properly oriented solar panels towards the sun. By 1967, the onboard chemical batteries reached a state of total depletion, and the transmitter ceased all activity. Ground engineers logged the mission as a total loss, assuming a tumbling satellite with a dead battery was a permanently broken system. Its suboptimal altitude placed the hardware directly within a high-radiation environment, subjecting the silicon and wiring to constant proton bombardment. The wiring logic error essentially shielded the satellite's internal systems, forcing LES-1 into a deep electrical hibernation. The satellite's survival relies on solid-state longevity. Discrete 1960s components possess a physical scale and durability that modern integrated circuits lack. Because the effects of space radiation were poorly understood in 1965, engineers overbuilt the hardware with heavy physical shielding. As the internal battery chemistries broke down over decades, the deteriorating metals physically bridged the terminals, creating a new, unintended electrical path. On the exterior, the solar cells maintained enough structural integrity to generate current despite 50 years of micrometeoroid impacts. The vacuum of space functioned as an oxygen-free vault, preserving the high-purity metals from oxidation and decay. This historical durability contrasts sharply with the planned obsolescence of modern orbital technology, which is built for short-term deployment and rapid replacement. The 237 MHz transmitter remained a discrete solid-state unit, requiring only a completed circuit and a power source to resume operation. The vacuum of space preserved the electronics in a functional state, waiting for a mechanical trigger to re-engage the system. That trigger was provided by orbital tumble. Over 50 years, continuous solar radiation pressure against the metallic hull slowly altered the satellite's rotation. In 2013, the rotation hit a precise geometric alignment, pointing the surviving solar panels directly at the sun. The resulting current bypassed the dead battery block through the internal metal bridges, finding a direct path into the satellite's transmitter. Receiving this power, the unit immediately began broadcasting its original 237 MHz telemetry signal. The rhythmic thumping detected on Earth matches the satellite's physical rotation, with the transmitter powering up only when the panels face the light. Even with a weak signal, the 237 MHz frequency is physically capable of piercing the Earth's ionosphere for ground detection. Decoding the telemetry confirmed a broadcast from a machine that had been devoid of power for nearly half a century. This resurrection resulted from a geometric and electrical fluke, a perfect alignment of solar pressure and hardware decay, 50 years in the making. LES-1 is merely the most visible example of a broader, silent network containing thousands of dead machines in orbit. Other systems have exhibited similar behavior, including the Transit 5B5 navigation satellite and the nuclear monitoring Vela satellites. Much of the early hardware launched into space shares this over-engineered, discrete design, making it likely that many other systems remain dormant today. This industrial graveyard represents an estimated $100 billion in obsolete technology cluttering vital orbital paths. These silent machines accelerate the risk of Kessler syndrome, acting as permanent collision hazards that cannot be maneuvered from the ground. Because they were built before the miniaturization of aerospace components, these Cold War-era satellites are physically larger and more durable than modern hardware. Unexpected transmissions from these machines also present a risk of electromagnetic interference with modern data relays and military frequencies. Modern hardware, such as this Spire satellite, relies on high-density circuit boards and delicate sensors that prioritize performance over multi-decade survival. The heavy logic of 1965 absorbs radiation damage that would flip a bit and crash the fragile integrated systems used today. If we detect a signal from a 1970s-era platform tomorrow, we must consider the implications of an unmanaged orbital history that refuses to stay silent. The signal from LES-1 serves as a diagnostic warning. Our unmanaged orbital history is waking back up. Today's sky is dominated by disposable constellations like Starlink, appearing here as a diagonal trail of white dots. Aerospace philosophy has transitioned from building for extreme survival to prioritizing high-volume replacement and safe atmospheric disposal. The vacuum of space functions as an oxygen-free vault, preserving high-purity metals from oxidation and decay. Physics dictates that LES-1 will not be an isolated event. Solar pressure and shifting mechanics will eventually wake other dormant solar arrays. The ghost orbit is a permanent feature of human industrial history that requires active monitoring. The forensic gap analysis is conclusive. A 1965 wiring error and 50 years of solar pressure combined to generate a signal in 2013. Engineers at the Lincoln Lab built hardware that outlived their own mission parameters, leaving a legacy of persistent circuitry. In a century, will our modern integrated machines be as persistent as these ghosts from the 1960s? The silent network constitutes a massive, highly preserved technical system holding vast amounts of dormant energy. It is an unmanaged web of historical paths circling the globe. Space freezes our machines in place, waiting for the next tumble into the light.